So now let's do a summary of our model and the data. So first, the data we have is first the treatment group, treatment data, which contains, let's call it TRT1, there are 10 treatment groups. They are IID, means independently identically distributed as normal distribution, with mean is mu1 and variance equals to sigma 1 square. So that's the first part of data. The second part of data is control. So in the control, so again we have eight normal mu2 sigma 2 square. Okay, that's our model and the data. So like what I said here, treatment group has 10 students and control group has 8 students. Okay, and our parameter are mu1 sigma 1, mu2 sigma 2. Okay, now we can just write, we already know what is the likelihood function and what is the what's the likelihood function? The likelihood is the probability of data given parameters, right? So in our case, it's just given mu and sigma, the data is treatment or control. So in our case, we assume that given those parameters, the treatment and the control are independent. So this likelihood actually can be factorized into two parts of likelihood. One, first part is about the treatment given mu1 and sigma 1 times the second part is the control right. That's the likelihood. Now again, we can just write down each part. Now each part is just a product of normal distribution, right? Normal density. So we can use, see here, we use d norm to find the normal density for each treatment. So it's a product. You can see this is our code. D norm for each of the this treatment. So you can TRT1, let's say we use TRT1 and the mean is mu1, standard deviation is sigma 1, right? And you can times, right, all the way to 10, because they are IID. You just multiply all the normal density together. Here, product, right? So this part, see this part, treatment group part. the product of it's normal. So in the function we call it likelihood function. This is our code. You can see that likelihood function take a argument as theta. Th means theta. And in the theta, we know mu1 is the first number in theta, sigma 1 is second number, mu2 is third number, sigma 2 is the fourth number. Okay, then what's the likelihood? Likelihood is a product of d norm, that's the density of normal, and we put the whole vector of treatment, right? And mean is mu1, standard deviation is sigma 1, times another product, right? Density of normal will control vector. Mean is mu2, sigma is standard deviation is sigma 2. Okay, so after we write down this likelihood function, we can check whether its calculation is correctly. So we can check, okay, what's the likelihood where mu1 is 10, sigma 1 is 3, mu2 is 10, sigma 2 is 3. Or you can change to other values. Okay, this is just so I can finish this. This is just shows you how to write down the likelihood function and why that's the case. So I think I will just make it. This part is for control group. Okay, this is how we write down the likelihood function. Okay, then after you write this likelihood, we need a prior, right? The prior is the prior actually is the marginal probability for parameter. So what's the parameter here? The parameter in our case is just theta, right? Theta contains mu1, sigma 1, mu2, sigma 2. Okay, what kind of prior we can put on this theta? Okay, then we can think about it. First, it's not based on anything. It's out of there. Okay, I'm thinking the prior should be something like this. That it's a distribution. I will put a distribution on mu1, mu2, because we know mu1, mu2 could be any real numbers, right? So I will use a normal density. Like a normal mean is 10, variance is 10 squared. I use this just because I really have no idea about sigma 2. I want to make it something like a uniform distribution. It's really uncertain, so you can change those values later after you write down the whole code and then run it, right? We can always include a sensitivity examination by changing those values and see if that will affect our final conclusion, right? And the distribution for sigma 2, I will use exponential because those sigma 1, sigma 2 has to be positive, right? So exponential distribution are always positive, and I make mean equal to 10, so the lambda is 0.1. And I can assume all the 4 variables are independent, right? Though they all independent of each other. So they're just nice, simple, just multiply density to get the joint density. Okay, here is this is the normal density, and this is exponential density, right? So see, I can say this thing is just equals to, so the density for mu1, because they are independent, right? Times density for mu2 times density for sigma 1 times density for sigma 2. Right? And we know that the first one, right? This one is just normal, so I just put the norm. That's d norm mu1, and the mean is 10, right? Standard deviation is 10. The first density, and then the second one is the same. Mu2, 10, 10. And then next one, sigma 1, sigma 2, they are exponential, right? So d exponential, where I put sigma 1, rate is 0.1. Right? That's the value for lambda. Then sigma 2 rate is 0.1. Okay. So this is clearly the R code for the prior of our case. The R code. So you see, okay, this is a prior function. Again, the function take argument of th, theta, and again mu1 is the first number of theta, and so on. And then, okay, first we need to check whether sigma 1 negative or sigma 2 is negative or not, right? If that's the case, they have to be positive. If one of them not positive, we return 0, okay, because it's something wrong here. And otherwise, right, if we do not return, if this is not true, we'll directly go to here. The prior is d norm mu1 10 10 times d norm mu2 10 10 times d exponential sigma 1 rate is 0.1 and d exponential sigma 2. So this is exactly the same as what I write here. See here? That's exactly the same thing. Okay. So the basic thinking was simply to choose prior for mu I that did not seem to prejudge which is bigger, and to choose priors that are well smeared out and sort of uniform over all even remotely plausible values, with the aim of letting the data, the likelihood, to produce any interesting features in the posterior distribution. Right? We don't want the prior dominate our posterior inference. We want to make the prior really weak, right? So that our data can tell what's going on here. Okay? So if we have doubts later or want to try with other prior distributions, just come back and change this function. You just change those values and rerun our code, and you get everything.